Hello friends, Mr. G here with a mini lesson on the basic logarithmic function. So let's begin with a connection between the exponential and logarithmic forms. When we have the exponential form b to the power of x equals y, this is equivalent in logarithmic form to logarithm base b of y equals x. These forms are inverse of each other. For our example, we have something like this. 2 cubed equals 8. And this is equivalent to log base 2 or logarithm base 2 of 8 equals 3. So we can think that the logarithm answers the question, what is the exponent needed to raise the base in order to obtain the given power? So when I look at the exponential form in the inverse logarithmic form, I'm asking this question. What exponent do I need to raise the base of 2 so that I get 8? And of course, the answer is 3. So we can think the logarithm is the exponent. The general form for the basic logarithmic function is this. F of x equals log base b of x, with the base b not being 0, greater than 0, excuse me, or positive, but not being 1. If we had a base of 0, that means that our everything would be 0 because 0 exponent anything is 0. Although we can talk about 0 exponent 0, but that's another topic altogether. And it cannot be 1 because the base of 1 raised to any power gives us 1. Similarly to what we saw in exponential functions. In that case, it was a. So this is the inverse function of the exponential function, say g of x equals b of x. As we explore the key characteristics of this basic logarithmic function, we're going to refer again to this connection between exponential and logarithmic functions. So let's look at the graph of an example. F of x equals log base 2 of x. And this is what the graph looks like. We have, instead of having the y-intercept at 1, our x-intercept is at 1. So the x-intercept is at 1, 0. This function, or the graph, is asymptotic to the y-axis. Our exponential function is asymptotic to the x-axis. The logarithmic is asymptotic to the y-axis. The domain can be any positive number, as we defined earlier, and the range, in this case, can be any real number. So we can see these things are reverse or inverse from our exponential function. What about the table of values? Well, when we create a table of values for a logarithmic function, I was being a little strategic about the values that I look at for x. So if you notice in this table of values, the values for x are 0, 1, 2, 4, 8, 16. And the outcome of this function is logarithm base 2 of x. When we look at this, we can see here when we have x being 0, the function is undefined. We explain that it is asymptotic to the y-axis. And the point 1, 0 shows us that that is the x-intercept. And we can look at the x values in this case that were chosen to be powers of 2. So it's easy for us to make that connection between the exponential and the logarithmic form. So we can see, for example, logarithm base 2 of 2 is 1 because 2 to the exponent of 1 is 2. Logarithm base 2 of 16 is 4 because 2 to the power of 4 is 16. Now, we're going to explore what happens when we have a fractional or a fractional base. We know we cannot have a negative base, but what happens when we have something like this, a logarithm base 1/2 of x? So just like we did for exponential functions, think of these questions. You can pause the video and think about them, and then we you can unpause it to see the answer. So what happens to the x-intercept, the asymptote at the y-axis? Do they change? What happens to the powers that we use in our table of values, to the graph? What happens to the table of values? So let's take a look at this. Well, the x-intercept remains unchanged. There's no change because 1/2 to the exponent of 0 is still 1, or the logarithm of 0 is 1 for any number. The asymptote remains as at the y-axis. This time we might be looking at powers of 1/2 instead of powers of 2. And we're going to look at what happens to the graph and the table of values in the following slide. So here is our graph for f of x equals log base 1/2 of x. Notice that the dotted purple graph is our original log base 2 of x. This black graph is the transform, not the transform, but the log base 1/2 of x. And you will see right away that this black graph is a decreasing function over the domain. It is a reflection on the x-axis of f of x equals log base 2 of x. We can see the domain, range, and y-intercepts are the same. The shape of the graph, however, is different. The table of values similarly reflects this. We still have the asymptote at the y-axis. The x-intercept is the same. And now we have powers of 1/2. So we can think of these, for example, if I look at the input of 2, the logarithm base 1/2 of 2 is -1, because if I take 2 to the power of -1, I end up with 1/2. So that is how we build a table of values for this example. So in summary, we can think of the basic logarithmic function is of the form f of x log base b of x, with b, the base not 1 and positive, greater than 0. And when b is greater than 1, we have a function that is always increasing. We talk about the domain and the range. The domain can only be greater than 0, and the range is any real number. When the base is between 0 and 1, then we have a decreasing graph, like we show here. The x-intercept is always at 1, 0, reverse from the exponential function. And finally, the graph is asymptotic to the y-axis, inverse of the exponential function that was asymptotic to the x-axis. And that is it, friends. Thanks for watching.